Hello everyone, welcome to another video on our healthcare data analysis playlist. In our today's video, we'll be looking at exploratory data analysis and we'll be analyzing patient heart data sets. The objective for this project we'll be checking for missing values and making decisions on how to handle them. We will generate categorical variables with age. We will carry out exploratory analysis of the data. We will review numerical variables and scale variables if necessary. And we'll also answer some questions. Are there variables that have some degree of symmetry? If they are, we apply some transformation to have a more symmetric variable. And also, are there categorical variables in the data set? If they are, we're going to pass them to numbers. This project is actually a real-world data set and is a project which I carried out for educational purpose. So ensure to stay with me as I walk you through how I went about analyzing this project. So without wasting time, let's dive right in. The first thing I did was to install and import the libraries which I'll be needing. So I imported Pandas NumPy as NP. Also, I imported my SQL.connector as SQL since this data set was saved in our MySQL database. So I would have to connect to the MySQL database for me to be able to access my data set. I also imported Matplotlib.pyplot as PLT and Seaborn as SNS for visualization of our data. To be able to gain access to our data sets, I will have to create a SQL connection and connect to the database, and I use this line of code to do that using the SQL.connect. Remember, we have imported my SQL.connector as SQL earlier on. So after creating this connection, the next thing I have to do now is to read in the file as a data frame. I have to use the pandas pd.read_SQL_query and pass in this. I want to select all rows of data from the @dt. This was the database name, and this is the name of the data on my SQL database on my system. After doing that, I just had to use pd.dataframe to convert my data to a data frame object and use the .head method to look at the first 5 rows of my data set. If you look at this is the top 5 rows of my data set, and you could see we have the age column, sex column where we have 1 and 0. We have chest pain, rest BP, that's your blood pressure at rest, cholesterol value, FBS for fasting blood sugar, ECG at rest, and the maximum heart rate, angina on exercise, old peak, slope, CA, that's for calcium, TAL, and AHD. Looking at the shape of our data set using the dot shape, you could see that we have 229 rows of data and 15 columns of data. First thing on our list is to check for missing values and make decision on how to handle them. So let's look at how I went about that. For checking of missing values, first of all, I used the .info method to look at my columns. I wanted to see if I had any missing values in any of the columns, but using the .info method, you could see that we have non-null values. So we had 299 rows of data for each columns. To check for missing values, I use the .isna.sum method. Using the .isna method is going to give you information regarding if you have missing values in your data set, and adding the .sum method to it is going to give you a summation of the missing values you have in your data set. So if you look at it, we don't have any missing value in our data set. We have zeros in all the columns, right, which is confirming the information the .info method gave to us earlier. The next thing we had was to generate a categorical variable with age. And if you remember earlier, our data set, we had age and it had different age numbers. So I first of all use the .n unique to check the count of unique ages. So we have 41 unique ages, and I use the .unique to see these different ages. So we have from age 63 and so on. To do further exploration of our age column, I have to use the .describe method, and from this you can see our minimum age is 29, the maximum age is 77, and the age on average is 54, and you can see other information we got, the standard deviation and all that. The next thing was to create bins for the various age category. I created 4 bins for the various age category: young adults, middle age, older adults, and elderlies. And to be able to do that, I use the 25% quantile, our median value, our 75% quantile, and our maximum value. So you could see the reason why I had to use the .describe method earlier. The next thing was to create labels for the various age categories. We use young adults, middle age, older adults, and elderlies, and our bins which we've created from 0 to our 25th quantile is going to be young adults, while from our 25th quantile to our median is going to be middle age, our median to 75th quantile is going to be older adults, and 75th quantile to maximum is going to be our elderlies. Okay, so to create a category column for age, we just had to use the pandas.cut method, passing our age column and the labels which we've fixed already, and our bins also. So when I was done with that, I tried to see what our new age category column looks like now. Looking at the age and the age categorical column, we have the elderlies, the young adults, the older adults, etc. I also created the visualization for our age category column. You could see that when we looked at both columns side by side, we could not get all the informations, right? I went ahead to create a cant plot so that I could see which of these categories occurred more. So you could see from our visualization that we had more young adults, followed by middle age, then elderlies, and older adults. When I was done with that, I gave a brief report on what I have carried out. We've tackled 2 objectives already: data cleaning and categorizing our age column. So the data set contained 299 rows and 50 columns, and these were what I did to the columns. First of all, from the graph above, it shows that there was no missing data. The data types were changed to the accurate types when necessary. We created a new column containing age categories. At the end, we add 299 rows and 60 columns. We created an additional age category column. The next thing on our objective is to conduct an exploratory data analysis, right? So let's go ahead and see how I went about resolving that. For our exploratory data analysis, the first thing I did was to look at the first 5 rows of our data once more. When I was done with that, I decided to also create a categorical column for sex column and angina column. For our sex column, we had 0s and 1. I decided to categorize 1 as male and 0s as female. And it was very easy to do that because I used the np.where. So this technically says where we have 1, let it be male. Any other figure should be female. So it's very simple for you to carry out categorization of column using the numpy.where function. We also did that for our angina column also. We said 1 to be yes and 0 as no. When we're done with that, I had to go ahead to view our data set once more, and you can see now that 2 columns have been added to our data set: the sex category column and the X angina category column. So you see we have male, female, and we have no yes in place of our 0s and 1 which we had earlier on. So to explore the various categorical column, I decided to create a graph using subplots. Using subplots, you can create different graphs in same space, okay, just like a dashboard in Python. I use the plt.subplot. So to do that, we have to create a figure and as is. So I use plt.subplot, and you have also to decide how many rows and columns which you want in your dashboard. So we need 2 rows and 2 columns. I also set our share y to be false and define our fixed size to be 15 by 8. This is the code I use in plotting our dashboard below. All you have to do now is to use the SNS Seaborn.canplot and create your graph. So you can see the lines of code I wrote to be able to create our different graphs. So if we go down and view our information, you could see this is chest pain. In this graph, this is a count plot, and wanted to see the various chest pain by their age category. So under our chest pain column, we have 4 different categories of chest pain. We have typical, asymptomatic, non-angina, and non-typical. So we want to see how it occurs between the various age category. So you could see the coloring: blue for young adults, orange for middle age, green for older adults, and red for elderlies. And if you look at this graph, you will find out that older adults had more asymptomatic chest pain, followed by elderlies. You can get more information from this graph. In this graph, we use a bus plot to show the distribution of blood pressure at rest with chest pain. While in this graph, we also did a count plot to show distribution of chest pain and the various gender, male and female. So you could see for asymptomatic chest pain, we have more male patients having asymptomatic chest pain, and you will have fewer female having typical chest pain. The next thing I did, I wanted to gather more information in relation to our various age category and the various genders, that's male and female. I wanted to see how many proportion of each of this age category made up the female and how many proportion made up the male. Using the dot values count and normalizing to be true, you could see for male we had more young adults of about 19%, while 18% of males were middle age, 17% were older adults, 13% were elderlies. For female, you can see that we had more elderlies. 10% were elderlies, 8% was middle age, 7% for young adults, and 6% for older adults. The next thing I did was to put this in a pie chart. Just looking at this table, we might not really get enough information we would want to get, but if we can visualize this or put this in a pie chart, we'll be able to get more information. So the next thing I did was to put this in a pie chart. So let's look at how the charts looked like. So these are charts, and with this, you know, a pie chart is usually 100%, 360, right? From this chart, you can see already that we had more males than female, and we could also see that we had more male young adults, followed by the middle age, older adults, and elderlies, while for females we had the elderlies, middle age, young adults, and older adults as the list. With just using a pie chart, we could get more information at a glance. The next thing I did was to use the dot describe method to describe our categorical columns. So for chest pain, you could see that the top category on our chest pain column was asymptomatic, while for thalassemia we had normal, for AHD we have no, the age category was young adults, sex category male, and X angina category is null as our most occurring category for each column. I had to visualize the information for easy understanding, and to do that I had to write a function. I wrote a user-defined function and I named my function the plot_cat_count function, and it's very easy. All I had to do was first of all create a list that contains these various column names, and now I'm going to create a for loop that's going to loop through our various columns name and create a count plot for them. So let's look at our graph which I created. This is the sex cat, and you can see the first column in our list is the sex cat column. Like we've seen earlier, the male gender is the highest in this sex category. You could see that we have about 200 rows of data as male, where we had barely 99 or 98 rows of data as female. So looking at our chest pain category column, you can also see that we had 4 different categories, with asymptomatic as the highest, followed by non-angina, non-typical, and typical as the least. Also looking at the ex-angina category column, you can see we have no. Most people did not have ex-angina, while people lesser than 100 said yes. So same thing for the thalassemia category column and our AHD category columns. I'll be dropping the GitHub link to this notebook, and you can go ahead, copy the codes and run this at your own convenience. So the next thing I did here is visualizing blood pressure at rest by sex for different age category. So I want to explore the blood pressure at rest for our various age category. I use the Seaborn.catplots function, and I passed in the names of the columns which we'll be using. So our sex category will be at our X, while our blood pressure at rest will be at our Y value. Then, since we want to look at how the blood pressure value changes for the various age category, we'll set our column as age category. This our categorical plot is going to be showing us the mean values for the various age categories. So let's go ahead and look at it. So the first graph we have here is showing us the age category for young adults and the blood pressure we have for male and for female. Remember, we're comparing that for male and for female for the various age categories. You can see for raised blood pressure male, it's slightly higher than that for female, but you can also see that for female it's very small. Then for middle age, you can see that blood pressure for female is more higher than for male, and for female you can also see that it has more variation. So you can see that for older adults and for the elderly. The next thing I did is using the Seaborn cat plot also, but this time around I wanted to visualize cholesterol by sex for the different age categories. So the first one we saw earlier was blood pressure at rest. So now we want to look at the cholesterol for these various age categories. We can also see for male and for female. For young adults, you can see that the cholesterol value for male is more higher than for female, but female had more variance in value. Then for middle age, you can see that the cholesterol value for females is much more higher than that of male. If you look at elderly also, you can also see cholesterol value for female is more higher than that for male, and it also has more variation in its values. Also for older adults. So I decided to go ahead to visualize the relationship between the blood pressure at rest and cholesterol for the different age categories using the Seaborn plot, but this time around, since I was looking at relationship, I used the SNS.real plot to look at the relationship between cholesterol and blood pressure at rest. I decided to add extra information using the U to represent text category and the col extra parameter to represent our age category. So with this graphic, we can see the relationship between the blood pressure at rest and cholesterol value for our various categories: young adults, middle-aged, elderly, and older adults. So for young adults, you can see that the values are located just within this particular area, while for middle age, you can see that the values are a bit dispersed, and the increment in the blood pressure at rest does not necessarily mean there is an increment in cholesterol value. If we also look at our elderlies, you can see that as our cholesterol value increases, our blood pressure value slightly increases also. I gave my summary from my visualization. So I said from the visualization above, more persons, that's both male and female and across all age categories, experience asymptomatic angina, while few people experience typical angina, which is chest pain. I also said from the distribution of blood pressure at rest with angina, it shows that persons with high blood pressure had typical angina. Males tend to have chest pain than females, but this might be seen as a result of imbalance within the number of males and female for their data set. Remember that we had more males compared to female in this data set. Also, most males had asymptomatic chest pain. The average heart rate for female was slightly higher than that of male. On average, the female blood pressure tends to increase over the years than male. On average, the female cholesterol value also tends to increase over the years than male. There is a relationship between cholesterol value and blood pressure at rest. As cholesterol value increased, blood pressure at rest also tend to increase. So next, we'll be going ahead to answer our fourth question, which is review the numerical variables and scale variables if necessary. Let's go ahead and see how I went about answering that objective question. So first of all, I had to drop the my unknown column since it is not relevant to this data set. I also went ahead to describe the numerical columns in our data set. So using the dot describe, we could get the counts, that's the number of rows in these columns. We could also get the average value of each columns, the standard deviation, the minimum value, the value at the 25% quartile, 50%, 75%, and the maximum value. The next thing I did was to go ahead and visualize the information above for easy understanding, because most of the times when you have a whole lot of numbers, you might not really make sense of what this table is saying. But using visualization or using graph, you're able to get more information. So I went ahead to create a graph for this. I use the KDE plot. Let me go ahead and click on this so that we can see our graph in full view. So the KDE plot is going to show us how each of these columns are distributed. If you look at our age column, you would see that the shape nearly resembles normal distribution shape. You can also look at our rest blood pressure, our cholesterol column. For our ECG at rest, the values are between 0s and 2, so that's why we have this shape in our graph. So we have our maximum heart rate, the old peak, slope, calcium values, and you can see the various shapes. So now we'll go ahead and normalize and scale my variables, because from the graph you can see that most of these our columns, they don't have this normal distribution shape apart from some few like age, cholesterol, rest blood pressure, and all that. But before we go ahead and do that, we want to look at the variance in each of these columns. I use the .var method to do that. Using the .var method on the columns which you just want to see, you can see we have the variance for age is 81.3, which is quite high. For the rest blood pressure, we have 313.2, 0.4. We have our cholesterol. We can see the value of ECG at rest, the variance, the maximum heart rate, old peak, slope, calcium. So we'll just be scaling those columns which the variance values are very high, like age, rest blood pressure column, cholesterol column, maximum heart rate column. So those are the 4 columns which will be normalizing and scaling their values. To do that, I use the numpy.log function. I called the @df, which is the name of our data, and passing a list containing the names of those columns which we want to scale. When I was done with that, I checked the variance after scaling. So using the .var method once more on those columns, and you can see the difference now. You can now see that the variance in values have been reduced after scaling it. You can also use standardization to scale variables. So first of all, I showed you how to use normalization to scale our variables. Now I'll be showing you how to use standardization to scale variables also. I use the standard scaler from sklen.preprocessing to standardize our variables. I passed in the names of those columns which we want to scale into a list, and I saved that as our columns. So the next thing I did was to get the arrays of values. So I used the dot values to be able to get the arrays only, and call the standard scaler to fit and transform these x values. And I went ahead and print our scaled values. The next thing I did was to go ahead and print the scaled data frame as df. We've created a new data frame containing our scaled values. So you could see the new data frame which we have now. These values have been scaled. I also went ahead to check the variance after scaling these values. So if you look at our new data frame now, calling the .var method on it, this is the variance and it's much more lower. So that's how to use the normalizing or use the standard scaler to standardize your values. So I gave a brief report at the end. I said, based on the provided numerical variable information, it appears that some of the variables may benefit from scaling. Variables like age, rest blood pressure, cholesterol, ECG at rest, maximum heart rate, old peak, and calcium have different scales and ranges. Scaling is typically useful when applying certain machine learning algorithms that are sensitive to the scale of the variables. It helps to ensure that all variables contribute equally to the model and prevent any bias that may arise due to difference in scale. Therefore, to scale the variables, I'll be using 2 different techniques, such as standardization, that is subtracting the mean and dividing by the standard deviation, and normalizing to show how to scale variables. We should also note that you don't necessarily have to use both methods when scaling. You can either use the first method I showed you, which is normalizing, or use the standard scaler, which is standardizing, to scale your variables. I just wanted to show you the 2 different methods, or the 2 different ways you can go about it. Also keep in mind that scaling is not always mandatory, and it depends on the specific context and objective of your analysis or modeling tasks. So the next objective question is to answer is, are there categorical variables in the data set? If they are, we have to pass them to numbers. Going onward, I am using the normalized @df data. Okay, remember we've scaled our data using the normalization method, so I'm using the normalized @df data to continue our work. I first of all read the first 5 rows of my data set using the .head method. So this is how our data set looks like now after scaling, and I also went ahead to drop all columns that would not be needed. I dropped the age column since we've already created a age category column, and I also dropped the sex category column, the X angina category column also. So when I was done with that, these are our new data sets looks like. And why I dropped those columns is because we want to check if there are categorical columns in this data set and pass them to numbers. So since we already have some of these, like our age column, which we've already passed to category, we can now go ahead and use that our age categorical column and pass it to numbers instead of using our previous age column where we had various ages. Also, our sex category column, we had 0 for female and 1 for male. So we can now go ahead and drop that our sex category column and use our previous sex column which we had. So when I was done with that, this is the data set which we had at the end of the day. So at the end of the day, we have 13 columns. So to be able to pass our categorical columns to numerical columns, we have to use the pd.getDummies method to do that quickly and effectively. So I called the pd.getDummies on our @df, which is our data set. This is what we got at the end. After doing that, I gave a brief summary stating that after I passed the categorical variables to numbers, there was 24 columns at the end. Also note that the age column was dropped to avoid overfitting, as the age categorical column contains same information. So this is the summary at the end of this project analysis. So I divided this as summary into 12 parts, and we'll be looking at each one of them. The first one is the initial dataset overview. I said the dataset initially contained 299 rows and 15 columns. Secondly is the data processing step. No missing data was observed in the dataset. Corrected data types as necessary for accurate representation. Introduced a new column by categorizing the age column. Thirdly, we looked at post-processing data set. After pre-processing, the data set consisted of 299 rows and 16 columns. Then we looked at angina distribution, and we said asymptomatic angina was more prevalent across all age categories with fewer instances of typical angina. Next, we look at blood pressure and angina. We said individuals with high blood pressure tend to experience typical angina. Next, we look at gender differences. Male exhibited a higher frequency of angina than females, potentially influenced by data set gender imbalances. Most males experience asymptomatic chest pain. Next, we look at heart rate differences. We said average heart rate was slightly higher in females than males. We looked at blood pressure and cholesterol trends. Over the years, females showed an increase in both average blood pressure and cholesterol levels compared to male. Next, look at cholesterol and rest blood pressure relationship, and we said there was a positive relationship between cholesterol values and the resting blood pressure, indicating that as cholesterol values increase, the resting blood pressure tended to increase as well. Under scaling our variables, we said identify the need for scaling due to differing scales and ranges in numerical variables like age, rest blood pressure, cholesterol, ECG at rest, maximum heart rate, etc. We demonstrated the use of both standardization and normalization techniques for scaling. Also, to categorical variable transformation, we transformed the categorical variables into numerical representations, which resulted in a data set with 24 columns. For the age column handling, we said the age column was dropped to prevent overfitting, considering redundancy with the newly introduced categorical age column. This exploratory analysis provides valuable insight into the data set, showcasing patterns, trends, and potential relationships. The pre-processing steps and visualization contribute to a better understanding of the data, setting the stage for further analysis or modeling tasks. This brings us to the end of exploring our art data set. If you found this video educative and useful, please leave a like. Also, drop your comments and question in the comment section. Leave your suggestions also. I'll be going through each and every one of our comments. And please endeavor to subscribe to my YouTube channel for more content relating to analyzing healthcare data. See you in our next video, and bye for now.